I'm the chair of the session number 4, and Dr. Waradej from Thailand, University of Chiang is helping me as a co-chair, and he's going to grade the presentations. In this session, we are going to have 6 papers, but we are going to start with a keynote speaker, which is Professor Santanu from Indian Institute of Technology, Bombay. And Professor Santanu is going to talk about power pinch analysis. And after that, we are going to start with our papers one after each other. After the keynote speaker, I'm going to introduce the other papers. Professor Santanu, if you are ready, everything is yours.
Thank you, Professor Reza. Let me share my screen. Is it visible? Yeah, thank you. So let's start. Today, next 20-25 minutes, I'll be talking about power pinch analysis. And so I'm Professor Shantanu Bandavadda from Department of Energy Science and Engineering of IIT Bombay, India. First, I'll start with acknowledging my sincere thanks to the organizers of 3rd International Conference on Energy and Power, with a special thanks to Professor Firoz Alam. And I'm also thankful to all my national and international collaborators for developing these theories, all my colleagues and staff of Department of Energy Science and Engineering, IIT Bombay, as well as my students. We have all learned essentially through the students and their work. So let's start with first heat exchanger network, where this originally pinch analysis was proposed. So if we look at historically, the first paper that we could find out appeared in 1944. And that's the first known heat exchanger network related paper. And in 1968, Professor Rudd came up with a beautiful concept called decomposition analysis, where he demonstrated for heat exchanger network, but in general, it's applicable to any engineering system. If the system becomes complicated, you divide it into small part and start solving in that way so that you can address. Remember, this is pre-computer era. So people try to look at smaller problems. In 1971, there is an important thesis came from Mr. Homan, and he essentially proposed everything that we know today as pinch analysis. However, his attempt to publish in journals were turned down because of whatever. Maybe energy conservation was not seen in 1971 as an important aspect. Use of algebraic method compared to a graphical method compared to computers was not very popular in 71. That time computers started coming in. However, in 78, 2 independent papers came, one from Lenov with his PhD supervisor, Professor Flower, and Dr. Umeda from Japan. And that's where we'll say that that's the starting point of pinch analysis. And later on, few interesting work came, how this design can be actually achieved. And in 2001, Furman with Professor Shamides proposed that this problem is an NP hard problem. So basically, we should use the Rod's decomposition principle for industrial level problems. However, what is this pinch analysis? So let's start with a very simple flow sheet. There is some feed goes to the reactor after heating it up, and the hot reactants are all coming up. You have to put in a distillation column, and get the distillate as well as bottoms. You need to cool them down. The question is, can we do some amount of heat exchange so that we can reduce the utility consumption? So this is where it started, like you can place them only the exchanges, only the streams. So H1, H2 are the hot streams and C3, C4 are the cold streams. We know their inlet temperature, outlet temperature. Can we place exchanges? Okay, so 1, 2, 3, 4 are the 4 exchanges. 1 is the steam heating and 4 is basically air cooling. And 2, 3 are process to process heat recovery. Now the question is, can we enhance the recovery? Can we reduce our utility requirement? Can we make it more energy efficient? That's a question essentially has been addressed through pinch analysis. So let's first start with the concept is, if there are multiple hot streams and multiple cold streams, how do I look at from a thermodynamic perspective? Okay. Can we add them? But addition is not actually mixing of the streams because they are of different compositions. Okay, and in a process that you have seen, like they have after distillation they have been separated. So if you mix them, that's gone. But we can add them in a mathematical and thermodynamic concept in a saying like how much heat is available from a hot streams or combination of hot streams, how much heat is required in a cold stream or a combination of cold streams. So that's the way it has been proposed. So if you look at H1 and H2, we can draw them in temperature, enthalpy. Enthalpy is not the correct word, it should be heat duty. Enthalpy and heat duty diagram. Again, temperatures are fixed. This enthalpy or heat duty is relative. That means we can look for the difference between starting and ending and say this much amount of heat duty is available. Now, if we add them thermodynamically, then we'll get a curve like this, where the first part is essentially from the lower segment where it is coming from H1. The middle portion is coming from H1 and H2 together. And the top portion between 125 and 175 is coming from H1 itself. So now we know that this yellow curve is essentially says how much heat is available as a function of temperature. We can call this as HCC or hot composite curve. So hot composite curve basically is a pseudo stream. It does not exist in reality, which is heat availability as a function of temperature. Similarly, we can do it for cold. The white curve is the cold composite curve, which says heat requirement as a function of temperature. Now, if we place them on the same diagram and if we place them too far apart, all the heat that are coming from the hot streams are is not to be utilized here in this case to the cold requirement. So they are, because they are too far apart. So all the heat available from the hot stream has to be removed by the hot utilities or cold utilities. And so the cost will go up. Now, if we place them too close, then these two curves might intersect or touch. If they intersect, then heat transfer is not possible based on second law of thermodynamics. If they touch, then also it is difficult because the area of heat exchange goes to infinity. So that means we need to have some gap. So what we can do is we can place them one by one with some difference in between. So there is a hot composite curve, there is a cold composite curve. And first we can identify that the overlap between them is process to process heat recovery. Okay, how much heat can be recovered? Because the overlap region of the hot and cold composite curve, heat is coming from the hot streams going to the cold stream. And because they are separated vertically, that means there is a temperature difference. We can see that the cold curve is extended on the right hand side. That means there is a heat requirement, but nothing is available. This we can identify as minimum hot utility requirement. And similarly, whatever the heat available on the left hand side from the hot composite curve, this heat has to be removed through external cold utility. So now this can be proved that this is the minimum for a given difference, and where these two curves come closest is known as a pinch point. So that's the starting. So I thought I'll give you a basic ideas about what has been done in the early 80s and late 70s. Now the concept is, or the question is, can it be generalized? Okay, and we are inspired from this particular quote from Richard Dawkins. Professor Dawkins says, some of the greatest advances in science have come about because some clever person spotted an analogy between a subject that was already understood and another still mysterious subject. So this question of analogy is extremely important. Can we find out that? So from there we have generalized and basically comes into the point of pinch analysis. There is no formal definition of pinch analysis. We tried to make a definition for pinch analysis, that is a set of systematic and algebraic methodologies with graphical representation for designing integrated production systems for sustainable development through resource conservation. Let me put this in a little better way. So in pinch analysis, we solve problems which are source and sink type. So that means we are given some sources. These sources comes with certain flow and some quality. And we have some demands which have some flows and qualities. We try to supply the flows from the sources to the demands subject to this quality constraint. Now it may happen that all the demands we cannot fulfill from the sources inside. This is reuse. We cannot reuse all the sources and demands may not be met. In that case, we need something known as an external source or resource, and we have to meet the demand, okay, subject to those quality constraints. And whatever the sources are available which are not used in the demand, we will go to basically and waste. So our objective comes is resource, which is external. You have to pay money for it. Can we minimize this? And design a network of allocations of the sources to the demands and resource to the demands and things like that. So this particular concept of source and demand has been extended in various applications. If we talk about flows, heat flows, temperature as quality is heat integration. It started in 1978. Mass as flow, concentration as quality, it is mass integration, water integration, hydrogen management in refineries, mass and properties, recycle streams, steam, pressure, cogeneration systems, energy, CO2, carbon constant energy planning, mass, time, it can be supply chain management, money, profitability is project investment. Then you can also have environmental risk planning and so on and so forth. This list is not exhaustive. However, today we are going to talk about for next another 5 to 10 minutes about energy as a flow and time as a quality, which is the power pinch analysis concept. So renewable energy systems or power pinch analysis was proposed from this idea. The basic things is we are given an energy demand, which is a function of time. And we have to design an energy generation systems such that we know the characteristics. It can be photovoltaic, wind, or a combination of them. And we want to find out that here time plays a quality role, and this is a directional quality. That means you have to generate the energy before you can use for the energy demand. And if you have generated too much before, that means we need to have a storage. So we have to size the storage also, what will be the appropriate. So what we can look at this is, suppose we are given, this is our demand curve. And we can look at the combined effect or cumulative demand over the day. And we can look at, say, photovoltaic. It's only available in the daytime. We can say what is the cumulative energy generated. Now, if you look at the initial portion, generation is low, there is a demand. And after that, there is more generation, but lower demand. But we cannot meet these systems unless we start with something original. So we can shift this curve upwards. And we'll say that OC, we can start with some internal initial storage requirement. We require some excess energy at the end of the day. Some of it can be used for the next day. And where they touch, it's become the pinch point or the power pinch point. That's the bottleneck, and we can optimize based on that. I'm not going into the simple differential equations. It can be written down in the differential equations. To the difference equation, it can be solved. However, here the problem comes is all the storage system, batteries or other things will have some kind of a losses, conversion losses and all. How do you take care of that? So it's better is if you look at what exactly is the storage energy. This is known as the grand composite curve in the pinch literature. See, this is the negative point, but storage energy cannot be negatives. That means we can identify the initial storage requirement. We can also find out what is the excess energy, and the difference between maximum and minimum can be the total storage requirement. So we can find out systems where what will be the initial requirement, what will be the storage requirement, and we can find out their trade-offs. Okay. So this is a simple way of looking at the trade-offs, where x-axis is the generator size and y-axis is your storage capacity. You'll get a sizing curve, and if you know their cost, optimize it. So in some sense, based on the local cost, based on the local variables, you can find out what will be the best design. So this has been applied to photovoltaic systems. Photovoltaic, you can get this kind of a generation effect. You can take even the temperature effect of the ambient and how it is going to play a role. There's little old data when the cost of the solar power was little high, but now it can come down significantly. This is almost 15 years old data that I'm presenting. We can also incorporate something known as an uncertainty, how the uncertainty plays a role out there, and we can look for it. So for a given reliability, we can see that how the sizing curve changes. The lowest one is a reliability of 50%. The topmost curve is a 95% reliability. So we can see that by increasing battery capacity, by changing the array rating, we can enhance the reliability of the system. So let me come to the concluding thought. So if I look at the brief history, this is Professor Budolenov in 1978 started the concept of pinch analysis through heat exchange network. This is Professor Lenov's colleague, Professor Robin Smith, who essentially introduced heat exchange network for batch process, also proposed for water minimization. This is Professor Mohammad El Halwagi. Professor Halwagi has basically extended for mass exchanger network, property integration. These are two colleagues of mine, Professor Dominic Fu and Professor Raymond Tan. They proposed energy planning. We have talked very briefly about the isolated energy systems of the power pinch, which we started from IIT Bombay and then used by many of our colleagues. And also with Dominic and Raymond, we started another concept of financial systems or financial pinch analysis. So pinch analysis was evolved over the time. It has been applied to various kind of systems for energy conservation to system level optimization. It has been applied to directly to the industrial problems. It has applied to various industries. Okay. Research potential is significant. It has been done in both industry as well as in academia. However, the industrial work are not coming out. We are only going to get from the academia. This is a dedicated journal for pinch analysis, process integration and optimization for sustainability, published by Springer and edited by me, Dominic and Raymond. Okay, you are welcome to send your papers out there. And to look at what is happening in the power pinch analysis, this has been applied to design isolated systems. It has been applied to various things, diesel battery, PV battery, wind battery, solar thermal, even photovoltaic thermal systems, combination of photovoltaic wind systems. Uncertainties, how it can be incorporated has been looked at and how you can optimize with that. And the figure on the left-hand side is basically how do you find out how to optimize for solar thermal systems. And on the right-hand side, it talks about wind battery systems considering uncertainties. So I'll end with a quote from a Bengali poet, Kavi Shukanto Bhattacharya. He died before the independence of India. And he essentially said, I take the solemn pledge of making this world a better place for the to be born. I find this is the very strong statement of sustainability when he said it in 1947. The book was published in 1948 called Exemption. And so that's all from my side. Thank you very much for your patience hearing. We have roughly around 7-8 minutes. If you have any question, comments, you're most welcome. Thank you very much.
Thank you very much, Professor Santano. Very interesting topic, and I learned myself very much from it. We have time for a couple of questions. If anybody has a question, our co-chair has a question. Please go ahead.
I just clap my hand, not raise the hand.
Yeah, okay, very well.
Sorry.
Very well. Professor Santano, well, to me, it was very interesting, and I understand that based on power pinch analysis, we have a better vision of demand, waste of energy, energy storage requirement, and so on. My question is how much this theory applied in Thailand? And if it is applied, how much money do we save by applying this theory?
I'm not sure whether it has been applied to Thailand, but this has been applied to some of the remote places in India, Australia, okay, and there is a significant work has been done in Malaysia as well. So there is a potential of significant savings. I do not know the data because everybody has applied to different places as this or similar kind of optimization technique. But we have applied to some of the industries cases, and we have shown that compared to their existing design, almost 30% money can be saved by using this theory for the solar thermal case. In case of solar photovoltaics, it has been applied to extremely remote place in Sundarban, and we have find out by using this concept and the analysis that comes after this. Just purely the theory is not enough because you have to look at the analysis. And by analyzing, we could show that by changing the operation strategy, we could save almost like 50% of the operating cost.
That's significant amount of money. I have another question. Me personally, I work in automotive industry. My question is that what would be the duration, time-wise, of this study for a company like, for example, Ford company, Toyota company, a car manufacturing company? If we are going to apply this power pinch theory in a small size, according to the size of a country, we apply to a car manufacturing, how much time do we need to study from 0 to 100, A to Z?
See, this concept, it does not require too much amount of sophisticated softwares and things like that. So even it can be done in a very simple calculator-based calculation approach. So the major time takes is collecting the data, finding out the reliable data, the production changes and how it affects the demand itself. But once this demand is there, and if you know some of the local radiations, wind velocities, okay, and things like that, it should not take too much amount of time. So the theory is very straightforward and comes very quickly, but the data collection takes more time. And then after that, planning, engineering executions, looking at the other aspects, which will take little more time.
It's good to know. And the amount of data that you say that it is needed to do a study, majority of those data have been collected in many companies, many factories, like power plants. They have data from the beginning to the end. So it's good to know that by applying this power pinch, you are going to save more money and more energy when it is going to be well developed around the world. Thank you very much. any final comment on your speech, sir?
Thank you very much. Thank you to you, Professor Zazar, as well as my co-chair. Okay, thank you very much. And thank you to all the participants.
It was an honor to have you here as a keynote speaker, and appreciate for your existence here.
Thank you. Thank you very much.
If there is no other question, we are ready to move on to our first paper here, which is submission ID number 3. It's about separation process of recycle of solar photovoltaic panels by microwave heating. And Dr. Chawanat from Maidol University, Thailand, is going to give us this presentation.
Good afternoon, everyone. My name is Chawanat Chalankasemvisuk, the representative of our topic is glass separation process from the recycling of the solar photovoltaic panels by microwave heating. So as you know, right now in our world, we have the generating capacity of the solar energy increased more than 80% significantly, especially in last few years. And for right now, the solar power accounts more than 45% is the new renewables. And according to the expansion in Asia, total solar capacity reached more than 78 gigawatt in last year. And according to these conditions, and also according to the Thai government policy, that we try to reach the usage of the sustainable energy. And according to that plan, to support, to encourage that plan, the EGAT, or the Electricity Generating Authority of Thailand, they plan to installation the solar floatings to all of the dams in Thailand. And that means that they want to operate about 2.7 gigawatt floating solar farms. And this means that more than 1 million solar panels will be installed on the solar in Thailand. And because of these amounts, the EGAT already known that the solar panel have the lifetime about 25 or 30 years old. So what happened after that? So this is the first stage. We try to form the sustainable platform to recycle all of these solar panels. So we do the literature reviews about the PV recycling. There are a lot of technique to do this recycling. We have the thermal treatment, we have the electrothermal heating, and also we have pyrolysis. And in this term, we also have the chemical techniques, the chemical treatment to do the PV recycling as well. But the first step, that before you use all of the layer of the solar panels to be recycled, we have to separate each level out together, which include the EVA, or the ethylene vinyl acetate sheet, and also the frames, the glass, and everything. So in this study, it is like the first steps. So we try to study how to remove the Thames gas from the PV panels. After we study in every previous research, we found out that one of very significant research is from Donny in 2012. The Donny used the radio frequency to heat up our panels, and then they claim that to delaminate the solar module can be done with the thermal treatment, and they use the radio frequency to heat that one up, and then the process of the remove gas will be more easy. And this is the result from the Donis in 2012. They create the radio frequency to the solar panel, and then they heat it up, and then they check about if they can remove the tempered gas from the PV panel or not. So according to that concept, we try to check about the economics analysis. Is it possible to make it in the factory size? And we found out that the radio frequency have very high cost to form, to operate in the commercializations terms. So we decide to change it in the same technique that we call the dielectric thermal process. So we try to heat it up with the microwave frequency. So this is our experimental procedure. We test the gas separation without heating first, and then we test the gas separation with the microwave heating and at the room temperature. So it means that we put it in the microwave and heat it up, and then let it go back to the room temperature before we test the force. And then we do it again at the control temperatures. And after that, to decide after this study, we try to decide the automatic line to recycle the panels. So we do the shape of the panels in the different shapes. The one thing that the last study didn't talking about is to check about the force of this process. So what we try to do is we try to focus on the force first for this one. We use the force gauge and the areas. Also, we check the temps between each level of the panel of our solars. So this is the first step. We test the gas separation without any heatings, and we found out that the average force per area is about 110.7 Newton square centimeters. So that is a lot of force. We have to pull this gas out, and we found out that with the high force, it can ruin the EVA levels, or it can ruin the other layers under the glass. So we test the gas separation after we put our solar panel in the microwave, and then we let it set in the room temperature. It's just a curious idea that I want to try that what happened. Is it the hypothesis that the heating, the frequency of the microwave will ruin the layer between the glass and the panel or not? So we found out we cannot decrease the force to pull the gas out. So we have to do some control temperature that we set it about 45 to 50 degrees Celsius. And we find out that at that temperature, which lower than the previous study, we can reduce the force from 100 to just only 47.5 per areas. So you can see the result comparison in these ones. After the demonstration, the demonstrating that the process around separating the broken card from the PV panel easier. we check the state of the EVA, and we found out that with the heating of the microwave frequency, they didn't lose anything for the EVA levels. So and we can reduce the force about 60% right now. So two conclusions, these experiments demonstrate the prospective option to the direct heat to the core of the PV panel using the microwave heating process. The results show that the temperature generally influence the separation of the glass fragments from the EVA layers for the solar panels. The dielectric heat of microwave involve the heating of the electrically insulating material by electric loss without destroying the characteristic of silicons and other materials. So this process may be enable different second life recycling process of the PV panels. So this is the first step. Now we study on the emissions during the heating process of this one, and after that we will try to form out the automation line to reduce to use in the factory sites to recycle to separate the PV panel first, and then after that we will continue to the whole process to recycle the PV panels. So I would like to thank the Department of Mechanical Engineering from both University, Mahidol University, and also Chiang Mai University, and also the company that provide the solar PV to us, the TSAT Excellent Engineering. Thank you.
Thank you very much, Dr. Shawana. It was interesting and very hot topic. We all know that PV panel has a big industry in front of it. We have time. If any of audience has any question, you can raise your hand. If not, I would like to ask Dr. Shawana to give us some cost analysis. We know that this PV panels still expensive, and to balance the amount of money that we are going to save takes time to recover the expenses. But I want to know the answer of this cost analysis from some expert like you.
I have to say that in the cost analysis in this process is ongoing because we not finished all of them yet. But as you know, for the renewable cost in every type of renewable cost, it cannot challenge with the fossil ones without any policy from the government. So I think the better way to push the sustainable energy in this world is the government should give some policy to encourage the usage of all of these things, like the ICEP models.
True, absolutely. Well, by using fossil fuel, we are destroying our environment. Everybody knows that. It's still very cheap. That's why we are still using it. And we have to pay the penalty by extra cost to use more renewable energy like solar and PV panel and so on. We all know that. My question was related to how long do we expect that this replacement happens in 20 years, 30 years, 50 years, that we stop using fossil fuel at all? That was my main concern. Yeah, any idea?
I have to say it in Thailand. According to the plan that I have some discuss with the ICEP. In next 20 years, they will cut out one power plant from the coal in the northern part of Thailand. So this is the another plan. So they try to produce more electricity. So I hope that in Thailand, in about 30 years, you can see the high percentage of the renewable energy.
Good to know. Very well. Thank you very much. I appreciate
you.
your presence here. That was very interesting topic. It's time
Thank
to
you.
go to next presentation, which is Dr. Rochana, if I am pronouncing correctly. Dr. Rochana is going to talk about an analysis of the potential use of photovoltaic. So the same topic, so probably can continue asking questioning from Dr. Rochana and bothering him or her, I'm not sure, about the topic that we were asking. So Dr. Rochana, if you are ready, we are ready to listen to your presentation. Dr.
Yes,
Rochana
I'm
is
here.
the lady. But yes,
Yes.
go ahead, please.
Yes, I already record my video. May I share the video I recorded?
Absolutely. I think we have to ask Dr. Chawana to stop sharing their screen. Excellent. Dr. Rochana, we are at your service. Please go ahead.
Do you see the video I presented?
You should click when you share screen. You should click share sound also, because I didn't hear anything.
Sound, I see.
Yes. Once again. Yeah, you must share it again and click on the left side. Yes, share sounds.
Good afternoon, lady. Do you hear?
Yes.
Yes. Thank you very much. And
Perfect.
gentlemen, my name is Rojana Prapainop from Kasetsart University Sriracha campus. Today, I'm going to talk about an analysis of a potential use of a photovoltaic system for an electric vehicle charging, especially in Thailand. This is the outline of my presentation. I'll start with the introduction, giving you the background of the study, and then I will define the objective, the method, and the scope of the study. After that, I will show the results and the conclusions. As you may know that the air pollution problem from the exhaust gas emission from the internal combustion engine vehicles has been raising awareness of people around the world to change their vehicles to the cleaner ones. And one of the promising clean vehicles is the battery electric vehicles, or BEV, as claim the zero emission from the vehicle. However, in Thailand, the electricity supplied by the authority is mainly based on the fossil energy power plant. Therefore, the CO2 emission as a product of the combustion process is still expected to release from most of the plant. The Ministry of Energy in Thailand estimated the CO2 emission from this electricity production in Thailand about 90 million metric tons per year, while for the transportation sector, the CO2 emission was about 70 million metric tons per year. These are quite a big number, actually. Therefore, the objective of the study was to analyze the potential use of a photovoltaic system, which is one of the clean technology for an electric vehicle charging in Thailand. We use the scenarios method with some of the statistical data. There's so many electric vehicle models, and there's so many specifications. So we select one of them for our analysis, which has energy consumption of 0.164 kilowatt hour per kilometer. 4 scenarios were analyzed. Scenario A, if the individuals use the electricity supplied by the authority which mainly use the fossil energy for their power plant. B, if individuals invest in a standalone system, a PV standalone system with a storage and use that to charge their battery electric vehicle. For scenario C, if individuals invest in their PV on-grid system and use that to sell the daytime electricity to the authority. However, they still use the main electricity from the authority to charge their BEV and to use for their appliance at home. And for scenario D, if the supplier invests in the new power plant to the PV system. We further divide into 2 subcases for different distance per day, 50 km per day and 100 km per day. We found that the approximate electrical energy consumption per day and per year was like this. And the approximate electrical energy bill per day and per year is like this. These numbers show that the electrical bills was about 1/4 of the gasoline price at the same driving distance. However, if we still use the fossil energy power plant, 1.4 metric tons of CO2 emission is still expected from the power plant. If millions of battery electric vehicles are used, millions of metric tons of CO2 may still be released from the power plant anyway. So this emphasizes the need for the clean power generation together with a clean vehicle to achieve the final aim of the clean environment. The scenario B, if individuals invest in the standalone system with the storage to charge their EV, the cost of this system with this storage is more or less the same price as the vehicle already. This could be used to charge only daily driving distance of 50 km per day, not 100 km per day. And the payback period is very long, even with the subsidy. So it's may not interesting for individuals, although it's good for the global environment. For scenario C, if individuals sell the electricity from their PV on-grid system to the authority at the daytime, and they still use the main electricity from the authority and pay the bills to the authority. This picture shows a home in Chonburi, Thailand that invest and install PV on-grid system on their roof. In 2016, they installed this system in their home in Chonburi province in Thailand. They invest about this sum of money, and based on more than 5 years data collecting from May 2016 to October 2021. The average daily electricity obtained from this system was 21 kilowatt-hour, or about 7,700 kilowatt-hour per year. Although they still have to pay for their bills to the authority, they will have the income from selling the electricity from their PV system to the authority. And I will show two different columns here with different selling rates set by the authority. In 2016 contract, the selling rate was 6.85 baht per kilowatt hour. But nowadays, recently, the authority dropped the rate to 2.2 baht per kilowatt hour. For the selling rate of 6.85 baht per kilowatt hour, the payback period is shorter than 10 years, which is good enough for individuals to invest because the lifetime of the PV system is about 20-25 years. But for the selling rate of 2.2 baht per kilowatt hour, it seems uninteresting anymore. These scenarios could reduce the CO2 emission. However, the main point is the selling rate set by the authority. And for scenario D, if the authority invests in the new power plant to be the PV system, they have to invest about 12,000 million baht for 400 megawatt. To sum up, after we consider 4 scenarios, we found that scenario A, individuals use the electricity power by the national grid, is good for individuals because there's no further investment from the individuals, but there's still some considerable amount of CO2 emission from the power plant that we have to concern. And for scenario B, if individuals invest in a standalone system with storage, this is not good enough in terms of payback period. And for scenario D, authority invest in the PV power plant. They have to invest about big sum of money for this plant. So in our opinion, we think scenario C, letting the individuals to sell the electricity from their PV on-grid system through the authority is the best for all stakeholders. However, the selling rate set by the authority has to be encouraged enough to encourage people to invest in this system. In order to encourage people to change the vehicles to the cleaner ones, the clean energy charging should be considered and further policy making is required. And this is the end of our presentation. Thank you for your attention.
Very well. Thank you very much. Appreciate that, Dr. Roshana. And
thank you.
Let me rephrase what I understood from your speech. I understood that you are thinking about the future that we are supposed to charge our electrical vehicle from our home place. And you gave us a scenario, 4 different scenarios, which one is the best for future option using PV voltaic panel to generate enough electricity to charge our vehicle. And you resulted that option C or scenario C is the best one. Am I right?
Yes, yes, indeed.
Very well. Thank you very much. That was interesting. Definitely, this is something that in the future we have to consider. Any question from Dr. Roshana? Okay, I appreciate the presentation from you, and if you have any other comment on your speech, please give us your comment. If not, then we are ready to go to next presentation. Dr. Rashana, any final comment?
No more any comments, actually.
Okay, okay, appreciate that. Thank you very much. We move on to the next presentation, which is actually paper number 36 about electrical and thermal application from solar energy to control the environment inside the closed straw mushroom cultivation house. That I don't know what that means. Definitely Dr. Pishator will give us information and enlighten the topic. Please go ahead.
Please share my video presentation.
You actually have a recorded. Yes.
You must share from by your own. Huh? Just press the share screen below. You see?
Pardon again, please.
Press the button, the share screen button below the screen.
I have to send a video presentation.
No. Share from your computer.
Okay. Okay.
Dr. Tishato, there is a green share screen button.
Yes.
Excellent.
I didn't hear anything. Would you mind share screen again and press share sound as well? Share sound. I can't hear anything. Okay.
Can you hear my sound of video?
No, that's very quiet, very weak sound, very weak.
Dr. Tishator, if you stop doing anything, I will fix the problem. Okay. I share my screen and this is your presentation. Is that right?
Yes, that's right. Today I'm going to talk about solar power cultivation and production of storm mushroom in a closed and controlled environment. I begin with the origin and objective of this research, then experimental end result. Storm mushroom production in Thailand exists from tree cultivation, outside, in basket, and inside the mushroom house. But inside mushroom house cultivation is the best for production because the environment is steady. The temperature and high relative humidity are ideal for growing storm mushrooms. According to research which provide information, the optimal temperature for mycelium is 30 to 37 degrees Celsius and fruiting body production is 20 to 30 degrees Celsius. Relative humidity for growth in the range of 70% to 90%. Many research interests in the mushroom house, like microcontroller and IoT, are used for communication and monitoring. The alternative solar energy using two greenhouses for net zero energy. This leads directly to the objective. The objective of research is designing solar energy for the conditions control system in the storm mushroom house that consists of electricity from photovoltaic and hot water for increased temperature from solar collectors. The total system was created for a standalone storm mushroom cultivation house. The gross mushroom house was around 24 square meters of area. The power for conditions control system is shown in table. Microcontroller with sensors, two ventilation fans, three water pumps. The total power is 0.216 kilowatts. The whole system consumes energy roughly 50% and works approximately 8 hours per day. Therefore, desire of energy for environmental control all of year is 315.36 kilowatt-hours. 2.5 square meters solar collector for hot water production and 385 watt monocrystalline half-cell solar panel. With 2 units deep cycle 6 voltage 220 mAh battery in series connection for electricity. This is schematic diagram of experimental setup. The hot water is used with a heat exchanger for increased temperature. The water spray system is used to increase relative humidity. The ventilation fan is working to ventilate air when the temperature, relative humidity, or carbon dioxide was higher than the condition, and the total system was controlled by a microcontroller with sensor. The solar energy system consists of two main parts. The solar panel transforms sunlight into electricity. Then electricity was transferred to the solar charger for use in the mushroom house and charging to the battery. The solar hot water system was from solar collector with 200 liters water storage. The overall water system was driven by a water pump. The energy balance is based on the first law of thermodynamics. The research has been focused on the solar energy harvesting, useful, and efficiency of the solar power cultivation and production of storm mushroom in a closed and controlled environment. The result of photovoltaic system at 8 a.m. to 5 p.m. The maximum electricity production and solar radiation was 287.1 watts at 1097.5 watts per square meters. The minimum was 30.09 watts at 124 watts per square meters. The average was 144.21 watts at 519.3 watts per square meters. The photovoltaic system produced 421.08 kilowatt-hour per year of electricity, and the average efficiency was 27.77%. The result of solar hot water system at 10 a.m. to 3:30 p.m. The maximum temperature water outlet from solar collector was 64.81 degrees Celsius, by water inlet 50.63 degrees Celsius, and hot water storage 51.03 degrees Celsius. The minimum temperature water outlet from solar collectors was 42.56 degrees Celsius, by water inlet 33.44 degrees Celsius. All-day solar radiation average is 881.67 watts per square meter. The efficiency of the solar hot water system was 40.17%. The conditions control in storm mushroom house was designed to use solar energy in the electricity and heat generation system. The requirement of electricity for the conditions control system is 315.36 kilowatt-hour per year. The solar panel produced 421.08 kilowatt-hour per year of electricity, that enough to use for the conditions control system in the storm mushroom house. The hot water production system produces hot water 200 liters, temperature more than 50 degrees Celsius. that it is used to environmental extract in mushroom house by a heat exchanger. At a final point, I would like to thank you. This research was funded by the Department of Graduate Studies, Office of Academic Administration and Development, and Renewable Energy Graduate Production and Development Project in ASEAN countries for graduate students from the College of Renewable Energy Major University. That is all of me. Thank you for your attention. Thank you.
Very well. Thank you very much, Dr. Tachatan. Because of difficulty that we had, if there is any comment that you wish to add, please give us that comment.
Again, please. Sorry.
I'm sorry. I am sorry, we are not on paper number 44 yet.
Sorry, again, please. Okay.
Hi, my name is Sai. May I proceed? Hi, are you able to hear my voice?
Dr. Sai, wait a moment. We don't
Yeah.
know what is going on. Who is presenting?
Mr. Techaton, do you have any comments for this conference? The chair session asks you, do you have any advice, have anything to say before you end your presentations?
About conference?
You have some comments, anything else to say before finish your presentation?
Yes, everything is nice.
Okay, okay, very well. Thank you very much. Appreciate that.
Thank you too.
Yeah. So it is time to go to the next presentation. There was some difficulty on internet. So it is time to go to paper number 44, which Mr. Sai Ratawik is going to present us. He's from Australia, University of Central Queensland. And the topic is about a systematic review on, what is that? Furtherance of
Furtherance of
thermal panel. So the same topic about PV voltaic panel. So we are going to start next paper. Dr. Sai, please go ahead.
Hi, firstly, I thank everyone and the ICEP committee for giving me this opportunity. My name is Sai Rutvik Madas. I'm a Masters of Research student at Central Queensland University. Today, I'm going to present a systematic review on furtherance of photovoltaic thermal panel technology. So the global energy demands are on a steep rise with the industrial activity and advancements in the developing and the developed countries. The electrical energy consumption has amplified from 16,771 terawatts per hour in 2005 to 25,021 terawatts per hour in 2019. In today's energy production, the predominant source of energy production is by burning fossil fuels. These fossil fuels release greenhouse gases into the atmosphere, which have multiple ripple effects on the environment. To control these greenhouse gas emissions, there is a dire need for sustainable clean energy source to replace fossil fuel sources. There are many clean energy producing sources, from which solar energy is one of the clean energy producing sources. Solar power that has a tremendous potential in meeting the current and the rising energy demands. If 90 minutes of incident solar radiation on the planet can be appropriately trapped and utilized, the whole world can be powered for a year. Such is the potential of the solar power. The photovoltaic panels harness sunlight to produce electrical energy, and the solar thermal collectors harness sunlight to produce thermal energy. So a photovoltaic thermal technology is one such system which concurrently produces electrical and thermal energy from the same source. A photovoltaic thermal system is a combination of a photovoltaic panel and a solar thermal collector. The working condition of a photovoltaic panel is similar to a solar thermal collector. Air or water is generally used as a cooling medium in this technology to dissipate the heat from the photovoltaic panel. So the electrical efficiency of a photovoltaic panel represents the electrical output of the panel given by area of the panel into the incident solar radiation. In general terms, it can be said as the amount of incident solar radiation that a panel can convert into useful electrical power. In the current conditions with the current technology, a typical PV panel has an electrical efficiency of about 18 to 24% only. And further, the main problem with the PV solar panels is with every degree rise in temperature after 25 degrees, the panel loses its electrical efficiency by 0.45 to 0.5% due to the rise in cell temperature. This is indicated by temperature coefficient of the panel. As we can see in the graph here, after 25 degrees centigrade, the electrical efficiency falls by 0.5%. At an outdoor weather condition at an ambient temperature of 25 to 30 degrees, the panel researchers found that the panel temperature is as high as 45 to 55 degrees centigrade. So a significant loss of almost about 20% of efficiency can be seen due to the rise in cell temperature of the panel. As I said earlier, the photovoltaic thermal system uses air or water as a cooling medium. The problem here is water or air is not able to dissipate the heat effectively from the PVT system. The optimum operating temperature range of a PVT system is 25 degrees centigrade, but the water is not able to dissipate the heat till a temperature of 25 degrees centigrade. So that is why we need developments in the PVT technology so we can achieve the set targets of the temperature region. A phase change material application and nanofluid application are the latest significant developments in the PVT technology. A phase change material is a latent heat storage substance that absorbs heat from the source without change in temperature. A phase change chamber, as we can see in the diagram here on the left, is attached to the PV cell back compartment so that it absorbs heat constantly from the PV cells. And this heat is again carried away by water into the heat exchanger and for domestic hot water applications. Whereas the nanofluid application is also a same type of application in which a nanofluid is prepared and pumped into the PVT system to dissipate heat from the PV cells. And this heat is again used for domestic hot water applications. So the objective of this study is to identify the key parameters influencing the performance of PVT systems with PCM applications and also key parameters influencing the performance of PVT system with nanofluids application. So the methodology used in this study is a systematic literature review process. The scope of this study is defined to nanofluids application and phase change materials, and the articles selected in this study are articles related to the application of phase change materials and review articles, and the time period in which the systematic review is performed is from 2014 to 2021. So the PCM performance shows that an efficiency enhancement of about 15% in an average, 10 to 15% on an average can be seen from the researchers. So these researchers, Matalla, Fu, and Alwali and Preet, have applied phase change materials and found that the panel outputs 17% more electrical power when compared to a panel without a phase change material application. And one interesting study here is conducted by Fu, who actually compared the PCM layer thicknesses and their effect on the electrical efficiency. So he compared the thicknesses from 1 to 7 centimeters. He found that the thickness had marginal effect, as we can see in the graph. Well, initially the PCM with low layer of thickness had a better performance, and as the time progressed, the PCM with high thickness layer had the better performance. This can be seen due to this variance of results can be seen due to the low thermal conductivity capability of the phase change material. And coming to the applications of nanofluid, nanofluid is again one other aspect where the PVT efficiency can be improved significantly. The nanofluids are basically made up of, as I said, particles from semiconductors, metals, and dielectrics. These are tiny particles with an average size of 20 to 500 micro nanometers. And also the particles are classified into a wide different variety. As we can see, many researchers have studied this effect using multiple nanoparticle types. And from the study, it is found that the particles with high thermal conductivity had the best performance within the tested range. So here, Alwali and Al Sharma, Sangeeta tested 3 different types of particles, each in their study, and they found that the particles with high thermal conductivity had the best performance. This is because the thermal conductivity obviously enhances the heat transfer rates in the nanofluid. And also another study contradicts the above results. Actually, the study conducted by Abed found that the TiO2 nanoparticle, which only has a thermal conductivity of 8.4 watts per meter square, has better performance than the others. This is because while preparing the nanofluid, careful consideration needs to be taken, because the particle attractive and repulsion forces and interfacial boundary layers also play a significant role. So the preparation definitely needs a careful consideration here to get better output results. And the volume concentration is also another important parameter in nanofluids application. The volume concentration actually defines the volume of nanoparticles, volume fraction of nanoparticles present in the total base fluid. As we can see, the results from the Sardabadi and Jia say that with the increase in volume concentration, there is an increase in electrical output efficiency. This is because the increase in volume concentration obviously has a high thermal conductivity and high heat transfer rate, so they perform better. However, the contradictory studies were also proposed by Hussein, Karami, and Abdullah. They stated that within the tested range of volume concentration, the particle with high concentration was not the best performer. This is because there is a possibility that although nanoparticles have high thermal conductivity, they have low specific heat, which upon high suspension into the base fluid will actually kill the heat carrying capacity of water. So particle volume concentration selection is a careful consideration parameter for better performance. This is a graph of the results showing from the Hussein. He actually compared water and Zn water nanoparticle at 0.1 and 0.2, 3, 4, 5 concentration, and the particle with 0.3 volume concentration actually had high electrical output from the panel. And next is the nanofluid flow rate. Flow rate is also an important parameter here, because flow rate, depending upon the flow conditions, is channeled into a laminar or turbulent flow. The flow rate, the increase in flow rate was found to be having positive effects by Moh and Hussein and also Sangeeta. So they have tested flow rate from 0.44 liters to 1.11. As they increased flow rate, they found the overall and the electrical efficiency had a significant improvement. However, Rahmanian, when tested the flow rate from 25 liters to 400 liters per hour, he actually found the best flow rate was at 100 liters per hour. The researchers stated that the increment in flow rate for marginal power gains is not profitable, as the amount of pump power consumed to increase the flow rate may actually exceed the useful energy gain from the panel. So flow rate is also an important parameter which needs careful consideration while running the PVT system. And in conclusion, I would like to say that the PCM and nanofluids have significant potential in enhancing the PVT performance, and nanofluid application has a better advantage over the PCMs. This is because the addition of PCMs into the PVT system will bring additional weight into the panel, which may not again be suitable for residential and industrial applications. Also, phase change materials are prone to leakage issues, etc. Of course, with the further research and development in this field, this will definitely come into play in the future studies. However, parameters nanofluid type, volume concentration, and flow rate are imperative when applying with nanofluids application, and these need careful consideration. Deriving optimum conditions for volume concentration, flow rate is a key component which can unleash the full potential from the nanofluids application. As I said, in the future, studies can focus on optimizing the volume concentration and flow rate parameter with nanofluids application. And also, future studies can focus on enhancing the thermal conductivity of phase change materials with better absorption rates. The research studies also show that the thermal conductivity of phase change materials can be enhanced by dispersion of nanoparticles itself into the phase change material. So this is another potential area which researchers can focus on. Optimum PCM mass and thickness layer must be evaluated for effective heat dissipation. Only few studies have focused on the thickness layer, so we are not completely sure how the effects would be. So future studies can focus on this aspect as well. Thank you for giving me this opportunity. Please feel free to ask any questions.
Very well. Thank you very much, Mr. Radwig. You were speaking super fast, and it shows that you are very well aware of what you are talking about, and you had enough practice.
Yeah, I actually didn't want to cross my time limit, so that's why I was just rushing.
Yeah. Okay. I guess that this topic is your PhD thesis project. Is that right?
Yeah. Well, yes. It's my research topic, studies topic. At the moment.
What is the objective of your research?
Of this conference paper or my PhD?
Your PhD.
My objective is to define the optimum concentrations for nanofluids application, like defining the optimum volume concentration and the flow rate, which can unleash the full potential with the nanofluids application.
Okay, this presentation that you gave us, how much of your study or objective was covered by this presentation?
I would say 40%.
40%.
Yeah.
Very well. It was very interesting presentation, and I appreciate your contribution. If you have any final comment for us, let us know.
No, I'm very happy with my presentation, and also I thank everyone for inviting me.
Sure. It was a pleasure to have you here.
Thank you. Thank you. Sure. I hope I enjoyed the whole session.
It was very interesting. Appreciate that. Okay. If there is no question from our presenter right now, we are ready to move on and go to the next presentation, which is going to be paper number 58. Presenter would be Dr. Wardaj. Dr. Wardaj is our co-chair. So he knows better than me what to do. The panel is yours. Please go ahead.
Okay, thank you so much. I have talked so much before about the technical problem. So right now it's my turn to give you a presentation. So hi everyone again, welcome to my presentations. So my topic is performance analysis of micro vertical axis Savonius wind turbine with the wind booster. These are my teams. Mr. Suradet Panyawong, Associate Professor, Dr. Niti Kamanglu, Mr. Nathawat Panasunthon, Mr. Sithikon Pantipa, Mr. Nermek Jijai, and I, Assistant Professor Dr. Woladet Manosoi. We are from Department of Mechanical Engineering, Faculty of Engineering, Chiang Mai Universities. So for about the motivation of this study, as we know that at present, the energy consumption demand is extremely increased. Thus, the widely used the electrical energy and fossil energy, or we call fuel, appear not to be sufficient. That's why we are trying to looking for a new source of energy. For example, the renewable energy is recently discovered and such as the hydropower, biofuel, and wind energy, but it's still not enough energy for the demand. In this study, we use the wind energy to investigate something. This is our objective of the studies, to analyze the micro vertical axis sourness wind turbine performance by wind booster. We use wind booster to increase the airspeed, increase the velocity of air, and increase the rotating speed of the wind turbine with the experimental method. So the results from the research can be applied for the wind booster for micro vertical axis sound wind turbine design. In this work, we did only the experiments. We did not do any simulations. If some of you interested, you can do it for us, if possible. So for the methodology, this is the S shape. We use the S shape vertical axis sourness wind turbine. A is the diagram we draw in the computer. B is the real one. We put the wind turbine in the wind tunnel. The wind tunnel test section, it's around 50 centimeters wide and 50 centimeter high, which is quite small. This is the wind turbine. We use the aluminum to build the S-shaped wind turbine. Figure number 2, this figure shows the wind booster that we mount in front of the wind turbines. This is the wind booster to accelerate the air velocity. So if you don't know that, these pictures show you all things that we have in our experimental setup. This is the wind tunnel sections. The air will flow in this direction with the red arrow. This is the S-shaped wind turbine. We mount the wind booster in front of the wind turbine. The airflow in this direction pass through the wind booster and pass through the micro vertical axis wind turbine. Below the test section, we mount the generator. These are technical data, around 60 watts, 15 volts with 12 magnets and 9 coins for each status. This is the technical data of our generator. This is an example of the angle of the wind booster angle in this study. We vary from 10 degrees to 90 degrees. This is an example of 10 degrees. This is parallel to the flow, but for 90 degrees, it's perpendicular to the flow with this one. This is the example. We vary every 10 degrees, 10, 20, 30, 40 to 90s. So now let's move on to the results. So we focus on 2 main parameters. They are the wind booster degree, we vary from 10 to 90s, and the wind booster number, we vary from 2 to 6. First, let's look at the first performance parameter, the rotating speed. As we've seen that if the wind booster angle increase, what happened? The rotating speed of wind turbine will increase with the increasing of the wind booster angle. But after 80 degrees, if we increase from 80 to 90 degrees, the rotating speed decreased due to the wind booster angle at 90 degrees blocked the airflow as is shown in this figure, this one view. This one was perpendicular to the flow, that's why the velocity decreased, the wind turbine velocities. The next one is the wind booster number. if we increase the wind booster number, of course, at the beginning, if we increase from 3 to 4, the velocity of wind turbine increase. But at the high wind booster number, if we put it more, it will block the airflow. That's why the rotating speed of the wind turbine decrease. That's why we have two main parameters: wind booster number and the wind booster decrease. This is the first performance parameter, rotating speed. And the voltage also. This phenomena also happen to another performance parameter, such as the voltage. It has a same way, same trend. So I will not explain that much. It's the same. The voltage also. The next one is the current from the generator. It's the same. Yeah, if same like rotating speed. Also, the output power of the generator. Yeah, if we increase the wind booster angles, of course, the velocity, the performance parameter increase. But if the angle is too high, like 90, it will block the flow, the velocity will decrease. Same as wind booster number. If we increase, if we put too much wind booster, amount of number of wind booster, of course, the velocity will decrease the airflow, and this will cause the decrease of the performance parameter. Also, tip speed ratio, pressure coefficient is again the same. The trend also the same. Nothing special. Yeah. So for the conclusions, as I told you before, the performance parameter increase with the increasing of wind booster angle. Since the high wind booster angle accelerate the airflow more than low wind booster angles. But the performance parameter decrease with the increasing wind booster number, because at a high wind booster number obstruct the airflow more than a low wind booster number. We have found that the lowest performance parameter were discovered at 5 wind booster and at 10 degrees, lowest one, because of the high wind booster number and low wind booster angles. The highest one we found at the 3 wind booster and 80 degrees because of the low wind booster number and high wind booster angle. This shows that we should not put too much, we should not mount too much wind booster and not to put wind booster at a high angle like 90 degrees. That's all for my works. It's quite short, sorry. So I open for your question. Thank you so much. So I
thank you very much. I appreciate that. Well, that is a very complicated system to optimize. There are millions of parameters, as I am going to talk about that. Although it looks very simple, and probably human was using this from thousands of years ago, still there are a lot of parameters to optimize.
Yes.
One question, you moved up to 90 degrees. Is there any limit on that? Can we go further, more than 90 degrees or not?
I think no, because there is no space anymore. I think, to move from 90. But I think if you have tried 90, I think it's going to be not better than 90.
Well, the question comes from this that you showed us 90 would be the best.
Yeah, sorry, 80. Sorry, 80.
80. Yes. Would be the best. Okay. So there is a physical limitation on increasing the number of degrees, so 90 degrees or so. The profile of the blade was semicircular, or an arc of a circle. Is that right?
Yes. Sorry, I may show again. Yes, in the presentation.
Sure.
It's not. Sorry. Can we share it again?
Yes, please go ahead.
Okay. You mean this one or?
Move on. Yes.
Okay. Yes, this is we just put only half of it because the wind tunnel is quite small. Yeah, we have no space anymore to put another circular. Like this.
My point was, go ahead to slide 7.
Yes. Okay.
Yeah, I see that the blade is an arc of a circle.
Ah, I see.
Is that right?
Yes.
Arc of a circle seems the first choice, simple choice. And according to my knowledge, actually, we had similar analysis, something like this, that Dr. Harun and Dr. Firuz
Ah,
in
okay.
RMIT, they did that for a student coming from Saudi Arabia, I guess, as a PhD project. So they did similar things to optimize and increase the performance. My point is that, can we do any other profile rather than circle or circular? The other question, I'm sorry, go ahead.
Yes, we can do it. Yes, of course. But we try only the circular one. Yeah.
The other thing is that, according to my knowledge, if you are going with circular, it is associated to a specific velocity of the wind to minimize the friction. If we increase the speed of the wind or decrease of the speed of the wind, then the friction will go higher. So every number of blades and any angle of the blade is associated to specific velocity of the wind. Am I right?
Yes, you're right.
So we didn't see here the effect of velocity of the wind in the performance of optimization.
Oh, we analyzed by the rotating speed of the turbine. I think it can tell something, the rotating speed of the wind turbine.
So rotation speed of the wind turbine was constant for all of your experiments?
Yes, this is look at this graph on the left side. This is a rotating speed. Yes, this one. It's yes, this one.
Well, again, as I said, this is a very complicated system, although it is very simple and kids can play with that. But scientifically, to optimize everything, it takes ages. It's not that easy.
Okay.
Appreciate that. Any final talk about this system? What is the future of this wind turbine?
Okay, the future system, yes, we would like to make the real wind turbine and test in the real place, like above the building or somewhere which is with a high wind velocity, like at the beach in Thailand. This is our next step. Yeah.
Very good. Good to know. Thank you very much.
And also we are looking for someone to do the simulations. Yes. If some of you in this section interesting, you can contact me. Yes.
Well, I'm keen to see the future of this research probably next year in our next conference. So we see what you have done by that time. Thank you very much. Appreciate it.
Thank you. I will still here until the end. So if you have any question, you can text me. Thank you so much.
I appreciate that. Thank you.
Because I'm the co-chair, so I need to stay.
Yeah. Okay. Very good. We move on to the next presentation, which is paper number 75, and Mr. Kiat Kong is going to give us a presentation on an efficiency study of hydrogen production by proton exchange membrane water electrolyzed cell coupled with photovoltaic thermal system. Wow, very complicated, and we are keen to see what is this research about. Please go ahead.
Yes, it's me. Firstly, can you hear me clearly? Can you hear my voice clearly?
Yes, we can hear you clearly. Yes.
Okay, thank you. Okay. Good afternoon, everyone. My name is Kiat Kong Winit Watanakun from King Mongkut University of Technology, Thonburi. So my topic today is an efficiency study of hydrogen production by proton exchange membrane water electrolysis coupled with a photovoltaic thermal system. It is quite long, but please follow me for this topic. Here, okay, firstly, why we need to focus on the hydrogen. Here you can see its property. The hydrogen will have a high energy density compared to the other solid biomass The hydrogen have approximately 140 megajoules per kilogram of the energy density, while the other solid biomass have more or less 50 megajoules per kilogram. And the hydrogen, it has a flexibility energy source because, okay, hydrogen itself, it can transform to the other form of energy like electricity by using fuel cell, or transform to the heat energy or other things, etc. And the third thing is they can avoid the curtailment because, okay, if you imagine we are going to use a huge number of the photovoltaic, something that harvests the energy from solar energy, then if you don't use it immediately, you will lose it. And that is the curtailment problem that facing in many countries like Australia, for example. Why don't we storage? Why don't we store that energy into other form like hydrogen? That is the choice. And then when we talk about hydrogen, and then for decarbonization, that is the roadmap for 2050 of European. We are going to the net zero worlds because we can produce the hydrogen from the renewable energy, that so-called green hydrogen. So what is the green hydrogen? The green hydrogen is the hydrogen that we produce from the renewable energy. Okay, let's see how we can produce the hydrogen. There are mainly two alternative ways to produce the hydrogen by using a fossil fuels. This is the traditional way to produce the hydrogen. They produce the hydrogen from like a steam reforming because the fossil fuel, it is a compound of the hydrocarbon, right? We remove the carbon and then we get the hydrogen. From this way, we produce the hydrogen from the renewable energy source by using the technique of water electrolysis or water splitting by separate out of the hydrogen and oxygen. As you can see here, as of now, presently, more than maybe 96% of presently we produce the hydrogen from the fossil fuels, while only 4% the hydrogen comes from this way, as we call the green hydrogen. Why it is like this? Because of this way, we can produce the hydrogen with the very low efficiency, and also the capex and opex of cost of the hydrogen producing is very expensive. That's why. So that is the objective why we need to focus to produce the green hydrogen by using the proton exchange membrane water electrolysis, which use the energy from renewable, the solar energy, coupled with PVT. PVT is the photovoltaic thermal system. And I will explain in the next slide why we use PV together with the thermal system to couple with the proton exchange membrane water electrolysis in this study. In our study, we have done the simulation in the MATLAB and Simulink software. It is widely used for modeling for the mathematical models. Here, this is the simple figure that we proposed in this study. You can imagine this is the PV mount on the household that can produce the electricity. Under of the PV, we put the thermal system, the heat exchanger here, the pipe that we can put the water here, pass through this heat exchanger under the PV. First thing, this water will cool down the PV panel in order to increase the efficiency of the PV. And in the same time, the water, after receiving the heat energy, it will increase itself of the temperature, which is the better for next system is the PM water electrolyzer. Because if we put the high temperature into this system, then we can produce more hydrogen. That is the win-win situation for couple PVT together with the electrolyzers. This is the system explained a bit confused, but here we have mainly two systems. This is the photovoltaic thermal system, and this is the hydrogen producing system here. For the photovoltaic system, we use a single model diode in this study. And this is the equation, the 5 parameter unknowns parameter. And then we use the thermal system network to analyze the thermal system underneath of the PV. And then here, the PEM water electrolysis. We use the fundamental equation here, the summation of our voltage, that the minimum voltage to enable this system to make a here to separate between hydrogen and oxygen. The configuration in this study, we use the PV module of KC2000 GT, the 200 watt PV module. The PVT sizing is about 1 meter times 1.5 meters. And then the absorber here, we use stainless steel with a square pipe to act as a heat exchanger here. Then the electricity is used for producing the hydrogen, while the hot water goes here to separate, and then we get hydrogen here. This is the model in our MATLAB simulation. Here we use the Simulink. This is the PV, how relation between each system. The temperature of PV will link together here, and then the electricity go to the PEM water electrolysis here. And then this is the energy from the PV. Then we know what is the temperature of the water out from the PVT go to the PEM water electrolysis. And this is the model here. This model, we assume that it is a quasi-steady state because we are going to simulate the whole year as an hourly average. Then we validate our model by using the previous analysis result to validate our model is work well. This is the IV curve of the PV that very close to the actual result here. And this is the trend of the thermal efficiency. This is the characteristic curve of the PEM water electrolysis. This is very close to the experimental one. After we confirm that this model is validated, then we do the experimental with our model here by vary the number of the PEM water electrolysis cell and see how many number of the cell that can produce the highest hydrogen. That means the optimal point. It is shown here that in this configuration, the 6 cells of the PEM water electrolysis can produce the highest hydrogen here. It is an interesting point that it is not the same point that the PV has the highest efficiency. This is an important one because we are going to use this one to introduce our novel controller afterward. Here we have done the value of the cooling water flow rate, because you know, if we put the very low flow rate to the PVT, then we get the higher temperature, which is very good for PEM water electrolysis. But the low flow rate, it can extract the heat lower than higher flow rate. If we can extract heat from PV, then the PV will increase its efficiency very well. That's why we need to vary here the cooling water flow rate in order to find the optimal point of the configuration. Then we found here on the 12th September 1 p.m. This is an example of 1 hour simulation here. Then we found that at this point, the 7 cells and 0.0014 kilogram per second of cooling water flow rate can produce the highest energy here. Then we have run along 1 day, and we found that here we used 2 simulations for tracking PVT and fixed PVT in our study also. After we get information how impact of the cells number and cooling water flow rate, then we introduce our novel controller to calculate the optimal thermal water electrolysis cell number for every hour in our simulation. Then the cell number can vary throughout the year to increase the overall efficiency. This is our objective as well. And you can see after implementing our controller, the hydrogen can be increased every hour. If you look at here, the operating voltage point in the blue line is shift down after implement the controller to the red line. For the green line, it is the maximum power point of the PV. As we showed you before, the operating point, the optimum operating point is a little bit above the maximum power point of the PV. Then we introduce the controller to achieve this one for both. After running the simulation for the whole year, we can conclude that our controller can improve the overall efficiency of 3.78% and 4.15% when the PVT is tracked along with sun's position and fixed position. This is how the energy transforms from solar energy to the hydrogen. Then the conclusion in this study, we show you that the PVT system coupled with the proton exchange membrane water electrolysis is the very good pair to produce the green hydrogen, since there is no emission from this system. It is compact and both systems can complement to each other as a win-win situation. Hydrogen yield can be increased as well the overall system efficiency by using our optimized controller. The efficiency can improve up to 4.15%. But in this study, as you know, we have done only the technical terms. In the next future, we hope that we should perform the techno-economic analysis to show that it is economical to use in the household application, as we mentioned before. Yes, thank you for your attention.
Very well, thank you very much. That's very hot topic in renewable energy. It's a dream of human to use solar energy to produce hydrogen, to use hydrogen as a fuel for storage of the energy. So any progress in this area is interesting to humanity as well. Yeah. Any question for our presenter? Very well. If there is no question, I should appreciate the presentation from the last one. Also, I thank everybody who presented the paper today in this session. That was the last one. So we are going to conclude this session, and I appreciate or invite you to join us again tomorrow morning using link number 1 at 9 o'clock for the opening of the second day of this conference. If anybody has any final speech, final talk, please share it with us. Also, I would like to thank our co-chair of the session. If you have anything to add to this session, please give it to us. Yes.
I have no comments. Yes, everything is okay. Thank you for inviting me as a co-chair session. Thank you.
Thank you very much. Appreciate that. Harun, you were very good backup for the session. I appreciate that you organized everything very well, and thank everybody. So we conclude the session and we close this, and I appreciate to see all of you tomorrow morning at 9 o'clock. Have a good evening.
Okay. Bye-bye, everyone.
Bye-bye.
See you again tomorrow. Bye.